I'm Kristinn Gylfason from the Royal Institute of Technology in Stockholm, Sweden, and I am going to tell you about our recent work on compact and low-power silicon photonics components based on MEMS. This work is a collaboration between 6 different European research institutes and companies within the MORPHIC project.
And the goal of the MORPHIC project is to extend silicon photonics with the MEMS. And that's what I'm going to tell you about today. So why are we interested in using silicon photonics for this purpose? Well, silicon photonics is a technology that allows and enables high-density photonic integrated circuits fabricated by CMOS process technology in a CMOS fab. So basically it leverages all the technology that has been developed for microelectronics and uses that for making photonics. So in this way we can achieve complex functionality, compact chips at low cost when we manufacture at high volumes. So in essence, what silicon photonics brings is scaling, and it allows us to scale up to, that is to say, we can fabricate on large scale, on large wafers in high volumes, but it also allows us to scale photonics down on the submicron scale because we have high resolution lithography and can make submicron waveguide circuits. And if we look at the development of silicon photonics in the last 20 years, we can see that this is actually happening now, this magic of scaling. And the number of photonic components on silicon photonic chips is doubling roughly every 18 months. But there is one difference between silicon photonics and silicon microelectronics. All the photonic chips currently are what we would call ASICs, or application-specific integrated circuits. So that means that they are all designed for one purpose. So for example, if we want to implement a 100 gigabit per second transceiver, we decide to use PSM modulation, we would have one design of our chip. And if we would want to have a different type of modulation to change or upgrade the link, we would have to basically design and manufacture a new chip. And yet again, a new chip if we want to change again the modulation. This is in stark contrast to how things are done typically in electronics. So in electronics, if someone has an idea for a new product or new gizmo, it's basically you go out and you select a field programmable gate array or a digital signal processor of choice. There are a number of standard components to choose from. And then basically we program this chip, implement what we want to do in this programmable chip. And then only if this product becomes a very big success, we would design a application-specific IC and have it manufactured by a foundry to have the sort of maximum performance possible. But for very many cases, the FPGA solution actually is enough. So the situation is very different from photonics. Today there exist no photonic integrated circuits that can be reconfigured using software to perform different functions. So essentially what the Holy Grail, what you would want to have is what we can call a generic programmable optical processor. So this is a generic chip that would include optical and RF interfaces that are then connected by a reconfigurable linear optical circuit that can be programmed to implement the desired functionality on demand. And it has actually been shown recently theoretically that any linear operation that will be needed in such a mesh can be implemented by just connecting together two fundamental building blocks, phase shifters and couplers. And at least one of them needs to be tunable. So if we have these fundamental components, we can build these flexible optical meshes where we can arbitrarily route light from one point to another. We can split light and combine again, and even start to create filter circuits based on interference, such as feeder filters based on Mach-Zehnder interferometers. So to realize this kind of programmable optical mesh, we need thousands of active devices in our photonic circuit to be able to build a reasonably complex optical circuit. So obviously then we need scalable circuits. So we need components that have very low power consumption, low loss, and a small footprint. And ideally these components should be manufacturable in a standard foundry process. So if we look at the different technologies available for photonic actuation, we can identify like 5 broad classes. And we did the analysis of these different options in the review papers I did at the bottom there. And as I mentioned, power consumption is a very important metric for scalability. And some of the most popular photonic actuation techniques today do very poorly. For example, thermo-optic tuning, which is very commonly used for reconfiguration in optical circuits currently, consumes way too much power to be able to scale it down and have thousands of components in a dense space. On the other end of the spectrum, we have techniques built based on nonlinear electro-optic effects. These effects allow us to make very fast optical circuits, and consuming very little power. But typically these effects are very weak, so we need very long and large optical circuits when we use these techniques, resulting in large footprint and larger optical losses. So when we consider the options, there is one technology, MEMS down here, or mechanical tuning of waveguide components, that looks pretty interesting. Now you of course think mechanics, isn't that way too slow to achieve reasonable switching times or tuning times in optical circuits? And actually the kind of mechanics that we are talking about here are faster than you think. So this is what we are talking about, are micromechanics or even nano mechanics. And these kind of mechanics, since they are very small and very little mass, can actually move them around very rapidly. So even on the microsecond scale, can achieve switching times with these optical MEMS down to the microsecond timescales. And this, for many applications, in particular the kind of programming that we are discussing here, is actually fast enough. You just need to set up the circuit using the MEMS, and then you would run your optical function on it for a good while before reprogramming. So in that sense, MEMS and NEMS is still also quite interesting. Another benefit of actually working on using silicon as a photonic material is that silicon is a very good mechanical material as well. And this is, of course, best illustrated by the success of silicon mechanical MEMS sensors that are now standard in all smartphones and mobile devices, such as smartwatches, training, activity trackers, and in the airbags in your cars and so on. And this is due to the this success is in a way due to, first of all, the very good mechanical properties of monocrystalline silicon, and also the low power electrostatic actuation that can be achieved. So here an example of a 3-axis accelerometer that draws only like 214 microwatts with everything, all the electronics and so on. And this is allowed to create novel types of products like smartwatches that have 1-year battery life, including such accelerometers. And a key feature of this silicon MEMS is the use of electrostatic comb drive actuators to achieve displacements. And these typically give us a kind of a quadratic displacement curve with applied voltage, as illustrated in this curve. So if you want to achieve a photonic tuning of a photonic circuit using mechanical displacement, there's basically, or we want to implement these, let's say, these fundamental building blocks using mechanical displacement. There are a couple of ways you can think about it. So the basic idea is that we have a waveguide where the light is guided, and the mode is a little bit deconfined. So part of the field, the evanescent field, actually is outside of the waveguide and can be accessed. So then if we come in, for example, with a slender beam of silicon that can be mechanically moved closer or further away from this waveguide, we can achieve a phase shift by modulating the effective index of the guided mode. And this can be done either in plane by horizontal displacement or out of plane by vertical displacement in one layer. Or if we have stacked layers, we can have another slender membrane moving on top of the waveguide. Tunable couplers can be similarly implemented by two parallel waveguides in a directional coupler configuration, where one of them can be moved either out of plane or in plane with respect to the other one to change the coupling between the two waveguides. And these kinds of circuits have been shown in the literature, and both of these types of devices have been demonstrated. But what hasn't been shown so far is actually integration of this kind of MEMS in a state-of-the-art silicon photonics foundry platform. And this is one of the goals of the MORPHIC project. So what we are doing is we are building on top of the ISIP 50G state-of-the-art silicon photonics MEMS platform of IMEC, and we are adding to that a couple of post-processing steps to enable the mechanical release of parts of the photonic circuits. And this work has been headed by EPFL in the MORPHIC project. So here are a few nice example pictures from the project. Here's a crossbar switch, nice array of switches. Here, example of a phase shifter, and some nice directional couplers with narrow gaps. So now I want to show you in a little bit more detail one of our devices. So this is a compact MEMS, silicon photonics MEMS phase shifter. So the device consumes only 60 by 40 square micrometer footprint on the wafer. And it's basically a suspended silicon waveguide, and in proximity to a narrow, slender silicon beam that can be moved back and forth using this type of comb drive actuator by application of a external voltage. So if we look in more detail in the waveguide cross section, we can see the refractive index tuning principle I was mentioning before. So the waveguide itself has a cross section of 400 nanometers by 220, and then there's a slender beam in close proximity that can be moved away from the waveguide in this case. So this is what we call a gap increasing actuator. And by doing that, the effective index of the guided mode reduces. So this simulation in the lower right corner shows that by this motion away from the waveguide, we can tune the effective index by 0.01, which would be equivalent to a temperature change of 100 Kelvin for a standard silicon photonic thermal phase shifter, which is, of course, not realizable in a real high density integrated optical circuit. Another nice aspect of this phase shifter is that it has quite a linear phase shift. So that comes from the combination of the non-linear, or let's say the balance of the non-linearity of the MEMS actuator, which has a kind of a parabolic actuation curve coming from the comb drive actuator. And that is balanced by the exponential dependence of the position due to the exponential shape of the evanescent field. So this type of actuator can have quite a linear response curve when we look at it, look at the phase shift as a function of applied voltage. So if you want to evaluate this kind of device, of course, what we do is we put it into a Mach-Zehnder interferometer circuit. And for this, we can leverage all the standard components of the ISIP 50G process development kit, or PDK. And then we can get these nice phase shift curves when we actuate with increasing in voltage. So the interference spectrum moves under the actuation, and from these kind of spectra we extract the phase shift and we get these actuation curves like in this picture here. And for this particular device we achieve 1 pi phase shift at 20 volt actuation. And of course we can play around a little bit with the design, and by the combination of a waveguide width, that's to say the confinement of the mode and the initial gap, we can have different level of phase shift reaching up to 2 pi here at just over 20 volts for one combination. And like I mentioned before, a very important aspect of this technology is the loss. From the contrast of this interference spectra, we can extract the insertion loss of these components. And for these devices, we get down to about 0.1, 0.2 dB per phase shifter. So if we look at this in context, so this type of performance in terms of the length needed for pi phase shift versus the insertion loss at pi phase shift, this device is already actually state of the art compared to what has been published on photonic MEMS phase shifters. So within the project, we are working on all the basic components. So here is work done at EPFL on couplers. It's a nice freestanding broadband coupler that shows good performance. So by combining, for example, the active phase shifter and such a passive coupler, arbitrary generic optical mesh could be implemented. And we are also testing different concepts for active couplers. Here is one that is a 1x2 single pole double throw optical switch using this kind of tip-to-tip couplers. And the coupling can move from port 1 to port 2 by electrostatic actuation of this tip. Another important feature of this platform is the low loss optical transits that we have implemented. So we want to be able to combine sort of standard cladded optical circuits using all the components of the IC50G PDK with our new MEMS components. And to do that, we have to transit into these suspended MEMS cavities. And here IMEC has developed a very nice low loss transit that has a loss of less than 0.05 dB per transit. So I think I've shown you that it is possible to actually realize these kind of reconfigurable optical meshes using these low power, low insertion loss and small footprint MEMS components in the nice foundry process IC50G of IMEC. So in summary, I would say that silicon photonics with integrated MEMS are a very promising platform for programmable photonics. And the photonics MEMS actuators, they can be monolithically integrated in the IC50G foundry platform. This we have shown already. And the performance of our components so far holds good promise for implementing now in the close future large-scale reconfigurable circuits in this platform. So I would be happy to take any questions you have after the talk, and thanks for listening.